This lecture, we will discuss the Hill equation and the hemoglobin oxygen binding. So the goal of this is we want to quantitatively understand the hemoglobin's cooperative binding to oxygen. Because we know that once it's bind, it's easier to bind more since they have like 4 spots you can bind. So the Hill's equation provides a model so that it says that okay, if you have effectively n number of oxygen binds to 1 hemoglobin protein, then we derive how it look like, and then it will give us equation, and it will give us an effective number, hemoglobin Hill number n. So this n is Hill's number. It means cooperative behavior of the binding. So it will then give us an equation which can fit this number and then give us an idea of like the bonding behavior. So this model meant to understand the dynamics of the binding that people may find useful. And then the discussion of Hill equation isn't limited to hemoglobin oxygen binding. Actually, in a biological like modeling, like the Hill equation and the method that we are going to discuss today is universal. So you will see it in a lot of other contexts of this type of modeling. So let's just focus on the modeling strategy instead of the subject of hemoglobin and oxygen bonding, because this oxygen bonding is just one example of this very general approach of doing quantitative analysis. So the general idea is if you have chemical reaction, it doesn't have to be like a oxygen binding. You can have any like a real chemical reaction. You have like a molecule A binds to molecule B to give you a molecule C plus D, whatever. You can always write a chemical reaction in this way. You have left side and you have right hand side. So in our context, we would have the left hand side is the hemoglobin with oxygen binding. So we give it a symbol as Hb and with O2 attached to it. And this N means the binding site. So in reality, one hemoglobin molecule can bind like a 1 or 2 or 3 or 4 or maybe 0. So it's maximally 4. And then for this modeling purpose, since we are looking for an like effective binding number or an average sense of binding, so this n can be a non-integer. It's just less than 4. So that's the n. And then it can dissociate. It can become a hemoglobin which is not non-banded, and then it give you release n number of oxygen molecule. So this model does assume that the multiple oxygen molecules bind simultaneously to a single hemoglobin molecule in a cooperative manner. So this is the hypothesis behind this modeling. So it's a simultaneous bind. It's not like a 1 step and then 2 step and then 3 step. So this is the assumption. And then we have K1 and K minus 1. They are the sort of like a reaction coefficient. And it's like so K1 is the rate constant for the dissociation of oxygen. And K minus 1 is the rate constant for binding of oxygen. So if you just look at this equation, you can write down the rate change of the concentration of the unbound hemoglobin. So now let's use this to denote concentration of a molecule. So this concentration is the square brackets is like concentration. It's sort of a convention in chemistry when people want to get the concentration of something. We have used the square brackets before to get the dimension. So you can tell what does it mean in the context of the discussion. You know whether we are referred to a dimension or we are referred to the concentration. So we will use this at some point just for ease of writing, or you can just write concentration C. It's up to you. In case the notation cause confusion, I will mention it. Otherwise, you can judge from the context of photo reader. So here, we mean the concentration of a molecule, or maybe of molecules, whatever. So we can know that the rate change in the concentration of the N-bond hemoglobin, it is affected in two ways. One is you can generate it from the forward reaction, means the dissociation of bonded hemoglobin with the rate of K1. So if it moves in the K1 direction, then the rate of change will be proportional to the concentration of the reactant. On the other hand, the reaction can go in the reverse direction, means association. Then the rate of like consuming hemoglobin would be usually it's minus K minus 1, the concentration of hemoglobin and the oxygen. So oxygen is to the power n because you can think about it, you have n oxygen adding up together on the right-hand side, and then you would take the product of the concentration of all the species on one side of the equation. So you will find that this type of modeling, like the concentration of a substance in a chemical reaction would be written this way. This is very, very common in a lot of scenarios. Okay, now at equilibrium, the net rate change in hemoglobin concentration is 0. So at equilibrium, equilibrium means it's no longer changing with time. So d dt equal to 0. Then it means the other terms are the same. So you can say under the hemoglobin concentration equal to kappa multiply the concentration of unbounded hemoglobin and O2 to the power of n. The kappa is just the ratio of K minus 1 divided by K1. So now we got this relation. Now recall our fractional saturation of the hemoglobin. So fraction of hemoglobin. We give it a name Y. I think we discussed it in the last lecture. And by definition, it's a fraction of hemoglobins that has oxygen binding to it. Or like, it's not the fraction of hemoglobin. It's rather like, well, you can think in that way. Yeah, maybe let's just think in that way. It's the fraction of hemoglobin that you have oxygen binding to it. So in the numerator, you have the concentration of hemoglobin that you have oxygen binded. And in the numerator, you have the total concentration of hemoglobin, which is the concentration of bonded versus non-bonded. Now you can manipulate this. So you can like divide both the numerator and the denominator by the concentration of hemoglobin. So in the numerator, like divided by this. The denominator you get 1 plus this ratio. Now if you use the result that here, use this relation, and you can get the ratio of this. So you would get like you are left with kappa and O2. You would have kappa, the concentration of O2 to the power of n, and then 1 plus kappa, concentration of O2, oxygen to the power of n. So if you wanted to write Y in terms of partial pressure instead of concentration, so you can use Henry's equation, place oxygen concentration with partial pressure of oxygen. Now, if you do this, you can write your Y in terms of the partial pressure, the PO2 to the power of n, and then we have P50 to the power of n plus PO2 to the power of n. Here, P50 to the power of n is defined by the Henry's constant of oxygen to the power of n, divided by kappa. This is not like we define it. This is just the result. So if you use Henry's equation to replace O2, then you just like manipulate the terms and clean it up. You will automatically get a term in the denominator, and we just call it a P50 to the power of n. So the P50 represents the partial pressure of oxygen at which hemoglobin is 50% saturated. So the physical meaning of this is the PO2 at which hemoglobin is 50% saturated. And just see that if you replace like a PO2 in the expression of Y, if you say let PO2 equal to P50, then you automatically get a 1/2 Y equal to 1/2. So that is obvious from this perspective. So this is the Hill's equation. So this is the Hill's equation. If you try to plot it, you will indeed get Y versus PO2 as this function. This is called a sigmoid equation. So the exactly like slope, for example, you may have a curve look like this, or you may have a curve look like this. Like you may have different slopes. Like the exact slope, like depend on n and also P50. So if you are doing experiment, you measure this, and you can sort of fit for n or like fit for many other numbers. And to fit for this, usually what people are going to do is they are going to like take a natural log of both sides. So let's so I'm just taking natural log. I'm not going to just write it down. So you can say log y. Wow. So, what you will get is log of y divided by 1 minus y equals to n natural log of CO2 minus n multiplied by natural log of 50. So now if you plot natural log of this versus natural log of CO2, and then you would get a straight line, and this slope is equal to n. So you need to get different like dots, and then just fit your linear line, and then you get you know what is n. N is we call it like Hill's cooperative number. So this is a linear relation. And then this type of curve, so the nonlinear curve, like the original nonlinear curve, you will see it a lot in biological context. So this is called sigmoidal shape. Sigmoidal shape. And I'm sure in other classes in human physiology or other classes, you will see this a lot. And usually the equations math behind this in a lot of cases is related to this type of Hill equation treatment. And if you like derive chemical reactions and you consider like forward rate and the backward rate of change, and then you derive an expression for some concentrations. And in many cases, you will get a sigmoidal shape. So hopefully that's what you can get for today's lecture, is the approach of modeling chemical reaction. All right, let me leave a homework problem for you. Okay, so this is the homework problem. So now consider a different model of hemoglobin and oxygen binding. So in the model we discussed in the lecture, it assumes like simultaneous binding of n number of hemoglobin, sorry, n number of oxygen to one hemoglobin at one time. And now let's consider a different model. But by the way, let me just mention, so from experiment, the Hill's number for that model was about was approximately 2.34. To just give you a sense of what's the result of the Hill's model. Okay, let's continue our homework. So now consider simplified model so that the hemoglobin is a heterodimer, meaning it has only two oxygen binding sites, 1 and 2. However, it doesn't bind simultaneously. So you can bind 1 or bind 2. So that means hemoglobin can exist in 3 states, either unbound or singly bound, or doubly bound. Now we assume it's two steps. So the two steps are given as you can see. The first step is you bind one oxygen, and then we had like a dissociation constant K1. This K1 is not the same as the K1, K minus 1 we discussed in the literature. We discussed in the lecture. In the lecture, the K1, K minus 1, they are lowercase k. They refer to rate constant. And if you see capital K, they are usually means like the equilibrium constant. So they are defined in a way that depending on how you define it. Sometimes people would put the reactant in the numerator and the product in the numerator and the reactant in the denominator. It's that's what the convention. However, in this problem, you can just assume the K1 and the K2 are defined in this way. So it's the concentration ratio between reactant and the product. So the K1 and the K2 are different, and these are two different steps. Now you can define the fractional saturation Y as the weighted average based on the number of oxygen molecular bonded per hemoglobin. So that means in the numerator, for unbounded hemoglobin, the weight is 0. And for singly bonded, the weight is 1, and for doubly bonded, the weight is 2. And then divided by the total available binding sites. So the total hemoglobin concentration, and you need to figure out how to express this HB total. And because each has 2 binding sites, then you can say in the denominator, that's the total available of oxygen you can bind. So that's give you the weighted average of oxygen molecules. The weighted the weighted average that represents the fractional saturation number. Then you are going to derive an analytical expression for Y. So you are going to derive an equation so that you can write Y in terms of K1, K2, the concentration of hemoglobin, unbounded hemoglobin, and O2. So you are only allowed to express Y in terms of the 4 parameters, K1, K2, HB, and O2, not the others. This is the homework problem.